Okay, everyone, welcome back after the coffee break. We have another session with a slightly mixed topic. We will continue on star and planet formation, and then we will have some talks on computational methods as well. As before, I will continue giving 3-minute warnings. And the first talk is by Raphaël, who will tell us about massive star formation, a tale of accretion, ejection, and multiplicity.
So thank you very much. So I'm Raphaël Mignon-Risse. I'm a CNES fellow at APC laboratory in Paris, and I will present you my PhD work that was focused on massive star formation and 3 questions in particular: so the accretion, ejection, and the formation of multiple massive stellar systems. And I will start by thanking my collaborators, which were Mathias Gonzalez, my PhD advisor in Saclay, Benoît Commerson, Yoki Rosdal in Lyon, and André Oliva and Rolf Klüper in Tübingen and Heidelberg. So first, I will start by some state of the art, just so you understand what has been done theoretically and numerically in the past 40 years, typically. So there is this historical problem, which is called the relative pressure or relative barrier problem, that says that when you have a 1D setup, a spherically symmetric setup, you cannot form a star more massive than 40 solar masses, because actually the luminosity increases with the mass, and at some point the radiative force associated with this luminosity is actually larger. So it's a repulsive force. It's actually larger than the gravitational force that allows the accretion. So actually the accretion stops. That's a problem because we know that there are some stars more massive than typically 100 solar masses. Fortunately, multidimensional simulations have shown that accretion could actually occur via a disk, so that then the radiation is released perpendicularly to the disk and accretion can continue. And this type of simulation have shown actually that stars of more than 100 solar masses could form. They have also shown the formation of so-called radiative cavities where radiation dominates. And some of those simulations have also shown that these cavities could be unstable to the so-called Rayet-Taylor instability, just like when you have water on top of oil. And that's something that I would not discuss today, but I would just will leave you the references here if you want more information on this debated mechanism. The main point here is that those simulations, they used, of course, hydrodynamics, and because of this historical problem of radiation pressure barrier, they also used relative transfer coupled to the hydrodynamics. And actually, in the past 10 years, people have been distinguishing the radiation from the star from the radiation from the disk, because both are emitted at very different frequencies, typically in the UV for the star, typically in the infrared for the disk. And because of that, they interact with the dust and the gas at a very different opacity. And when you only use let's say one radiation component, then what was done is that the relative force was actually very largely underestimated. So my first contribution was actually to implement such a hybrid method in Ramses. Now, if you want to let's say do the basic massive star formation calculation nowadays, it's radiation hydrodynamics. But if you want to also focus more on the observational constraint and how to meet the observational constraints with those simulations, perhaps one has to go beyond the absence of magnetic fields, for example. So what we know now is that disks around massive protostars are present. There are still relatively few constraints, but thanks to ALMA, in the past few years, people have been finding disks that are actually quite smaller than those formed in the hydro calculations. Second, the outflows, we think that they are unlikely to be only relative, because if we compute the force necessary to accelerate the gas up to the observed velocity, then as you can see here, actually the relative acceleration is too small by 1 or 2 orders of magnitude. And finally, we know that massive stars are more often in multiple stellar systems than low mass stars, and we would like to understand why. So to answer this question, we can actually study what could be the role of magnetic fields on those 3 questions, and in the final one, whether the massive stellar multiplicity is kind of due to environmental conditions that could then depend on the magnetic field strength, for example, or on turbulence. So to address these 3 questions, we will follow the collapse of massive prestellar core, that is 100 solar masses. It is magnetized, it is turbulent. When we say it's turbulent, it's actually we have, I would say, an easier model to understand, which is just some initial velocity dispersion to model turbulence. And then the physics which is included is the hybrid reactive transfer method, the hydrodynamics, and non-ideal MHD, just like in the simulations presented by Hugo before, with ambipolar diffusion, meaning the drift between the ions and the neutrals. And then we will consider 4 simulations. So just starting from this one, sub A, well, we have magnetic field that is moderately strong and turbulence that is subsonic. So this is the Mach number. And starting from this run, we will have a similar run in terms of magnetic field strength, but without turbulence. A similar run with supersonic turbulence, and a similar run in terms of turbulence level, but with stronger magnetic fields. This way, we have 4 simulations, 2 of them here in orange, where turbulence is super albenic, meaning that it dominates over magnetic fields, and 2 of them in which turbulence is sub-albenic, so it will be dominated by magnetic fields. So let's take a look at the density slices. Here on the left, it will be in the outflow plane, and on the right in the disk plane, starting from one of the 2 turbulence-dominated cases. So what we find is the formation of moderately large outflows and a binary system. Then we shut off turbulence. This is the no-turb run. We have very large outflows, a unitary system. Then we increase the turbulence so that it's super albenic, but also supersonic. We have, once again, a binary system and a very tiny outflow. And then we increase the magnetic field strength, starting from the first run. And we have very large outflows and a unitary system. So that when turbulence dominates, we have a binary system. When magnetic field dominates, we have a unitary system and very large outflows. So let's first focus on the accretion disks. We find that they have quite similar properties in them, especially on disk size, regardless of actually the turbulence of or the magnetic field strength. And they have also similar properties from one stellar component to another in multiple stellar systems. We find disk radii that are typically between 100 and 200 AU, which is much smaller than what was found in the hydrodynamical calculation, and which is basically the closest that we get in comparison with the smallest disks that have been observed so far. And this radius is consistent with magnetic regulations. You can check this paper by Patrick in 2016, which shows that it's actually the magnetic field that plays this dominant role in setting the disk formation. Now, second, let's focus on the origin of outflows. So to do that, we will take the non-turbulent run, which is the easiest one to interpret. And we will take a look at 2 forces that could launch outflows: the Lorentz force on the left and the reactive force on the right. And we compute the ratio between them and the gravitational force to see whether they are capable of launching outflows. And as you can see here in red, and here in red also, well, the Lorentz force and the reactive force can launch outflow. They dominate the gravitational force. However, when you compute the ratio between both forces, you find that actually the Lorentz force dominates over the reactive force, so that the outflow is mainly of magnetic origin. And this is true up to 10 to the 4 solar luminosities, and actually even 10 to the 5, even though you find that close to the sink in the star vicinity, the reactive acceleration dominates. But it shows that the magnetic, the massive protostellar outflows are mainly of magnetic origin. And this confirms the paper by Benoît Commerson more recently this year that was done with the FLD reactive transfer method. Now we can focus on this Lorentz force, and actually we can decompose it as the sum of a magnetic pressure gradient and a magnetic tension force. So we will focus on the first one. So what happens here? Well, you have the field lines that are initially vertical, and then you have the differential rotation that twists the field lines so that you produce a toroidal component that is absent above the disk, so that you have actually a gradient in this toroidal component. So it creates a gradient in the B phi and also in the P phi square, which is typically the magnetic pressure. And as you can see here, this magnetic pressure acceleration, it actually dominates over gravitation. So this is responsible for launching the outflows in our simulation. It's the so-called magnetic Tour flow. Now we can also wonder whether there is this so-called magnetocentrifugal acceleration. That's the mechanism that is one of the best candidates to explain the high velocity jets around a protostar, but also around black holes. And actually, in this case, the acceleration is not perpendicular to the magnetic field lines, but it's along the magnetic field lines. It taps basically in the gravitational energy to accelerate the gas centrifugally. And in this case, you have the presence of an acceleration region up to the Alfvén surface, where the gas velocity and the Alfvén velocity becomes equal. And actually, in our simulations, we find such a region above and below the sink, where the gas accelerates up to the Alfvén surface. So we have also an acceleration that is consistent with magnetocentrifugal acceleration, although we would need a final resolution to get converged results regarding this mechanism. And now let's focus on the multiplicity. We find that when turbulence dominates, we find that there is fragmentation into sinks, and in the end, it ends up in mass ratios that are quite close to 1, which is very interesting because actually in the universe, massive stars are very often with other massive stars. What is the origin for this multiplicity? First question. And second, what is the impact of magnetic fields and turbulence on this mechanism? Well, we find that actually the origin of multiplicity and fragmentation is spiral collision. This occurs via the collision between two subsequent spiral arms, and this is actually quite interesting because there was a paper by Tobin in 2016 that found a triple protostellar systems that was still embedded into spiral arm structures. And what we find is that if we take a look here at the disk radius as a function of time, and we plot as circles the time at which a secondary sink forms, it always forms just after a peak in disk radius that was actually due to the very large growth of a spiral arm. And from the orange to the red line, well, we have decreased the turbulence. That when turbulence was decreased, fragmentation was delayed. And similarly, between these ones and the blue one, magnetic field is increased, so that when magnetic field was increased, turbulence is delayed as well. So that what we find is that there is some opposite, let's say, behavior, opposite influence of turbulence and magnetic fields regarding fragmentation. When turbulence is there, it adds some angular momentum, so it contributes to the growth of spiral arms and to the fragmentation. And when magnetic fields are there, there is some magnetic braking removing the angular momentum, so it limits the growth of the disk and of the spiral arms, and fragmentation is reduced.
Yeah, it's your 3-minute warning.
Yep, thanks. And I will end with an ongoing project, which is actually we would like to answer this question: does the multiplicity depend on the code? And for that, we are working with people at Tübingen and Heidelberg that do not use Ramses, but they use Pluto. And one way to kind of decompose the question is, first, do we capture the fragmentation process? So in this case, it's a spiral arm collision. So it's a question of spatial resolution, of course. And then here we find that from 10 AU to 2.5 AU, and even actually 1 AU, this is all preliminary, but in the hydro and in the MHD case, we find kind of resolved, I would say, convergence regarding the resolution of the fragmentation. But in the MHD case, it's much more demanding because actually resolving the spiral arms in the individual disks is much more demanding. So of course, it's solely related to what has been discussed in the last question session. And second, the other question is, do we capture the evolution of the fragments? Because of course they will eventually merge, or their orbital separation will increase. And in our case, we find that actually with those initial conditions, and in this case, which is isolated, well, the orbital separation increases because of the angular momentum budget versus mass budget. And I will just finish on those conclusions. So first, we find that the accretion process is disk-mediated accretion with disk sizes that are much smaller than in the hydro case, that can so far only be explained with magnetic fields that are consistent with some of the observational constraints. The multiplicity of massive stars, it seems to be at least partly driven by the interplay between turbulence that increases fragmentation and magnetic fields that suppresses it. And finally, we find that massive protostellar outflows are magnetically dominated. And I will just finish on this.
Thank you. Any questions? See some applause. Jason. If someone could unmute you. I don't think I can. I can only ask you to unmute, unfortunately. Which isn't going to help. Johan, can you rescue us? There we go.
Yeah, perhaps Johan doesn't like me. Very impressive talk. So I was, so this is not my field. So my question could be very dumb. So my impression from Star Forge simulation, if you are familiar with that. No. Okay, but perhaps somebody correct me if I'm remembering the wrong name. So there has been a work by forgot his name, Phil Hawkins and collaborators, I think, and they started to implement these protostellar jets in their GMC scale simulation. And if I remember correctly, their jets are very prominent and very strong. That was my impression. Perhaps they could have just put it in by hand. So I was wondering, how strong your jets are in this star forming region. I mean, do we have to worry about in the GMC scale simulations, for instance, in terms of energy budget?
Well, yeah, one thing is that it's very difficult to resolve those jets, because basically the closer to the star it is, then the more gravitational energy there is to tap in. And actually the highest velocity component comes from this innermost region. So in our case, we are limited to 5 AU resolution. People in Tübingen have been actually working, I think they are currently working on this with less than basically sub AU resolution. In general, it ends up in jets that are like 100 to 300 kilometers per second. Then I don't know much more about, for example, the energetics of these jets and how much they would impact the parent cloud. Yeah, I'm not very familiar with the feedback on those scales.
Okay, thanks.
Okay. I think that puts us in a good spot to move on to the next speaker. So
thank you.
Thank you for your great talk. Can we have Omar sharing your slides, please?
Yes. Okay. So can you see correctly my slides?
Yes, we
okay.
can.
Nice. Okay, so hello everybody. My name is Omar Attia. I'm currently a first-year PhD student at the University of Geneva, but I'll present you my work of my master thesis of last year at the University of Zurich under the supervision of Romain Tessier and in collaboration with the Sphinx collaboration in general. So the issue of my presentation will be the Biermann battery, its role in explaining the appearance of the magnetic field in the universe, and of course, how I implemented it in the high performance cosmological simulation code, Ramses. Okay, so I will start with the question of the origin of the cosmic magnetic field, which remains one of the greatest unresolved problems in cosmology to this day. It's nonetheless widely accepted that its origin goes through two key stages The first one is the generation of a seed primordial magnetic field, while the second one is the amplification of this field in order to be compatible with today's measured values. And so different scenarios have been proposed to account for this primordial magnetogenesis. And the first ones rely on a primordial magnetic field that would have existed from the beginning, would have been created during QCD or electroweak, first order cosmic phase transitions or inflation or stuff like that. Another invoked process would have taken place prior to recombination. It was proposed that the primordial magnetic field could have been generated during the radiation-dominated era in highly rotating regions of the universe. But this idea is now considered as rather unlikely because of the rapid decay of vorticity modes when structure forms. And finally, the last class of mechanisms occurs during reionization, or the time of formation of the various first stars and galaxies. So during episodes of violent shocks between proto-galaxies and within ionization fronts caused by the birth of first stars, the resulting magnetic field, which is of the order of 10 to the minus 20 Gauss, needs to be subsequently amplified by galactic dynamo. And so it's all the more relevant to investigate the key phenomenon underlying these processes, which is namely the Biermann battery, which has the advantage of generating such seed magnetic fields from zero initial conditions. Okay, so first let's have a quick look at the important features of this physical phenomenon. As you know, the basic equation dictating the evolution of any magnetic field is, of course, this induction equation, which can be expressed as a function of the electromotive force. However, this equation taken alone is not capable of generating a magnetic field in a previously unmagnetized region, meaning given the initial condition B equals 0, the field will remain 0 forever. We hence need a third term to act as a source of magnetic field. And so the solution of the found by Biermann emanates from the equation of conservation of electrons' momentum. And so basically, Biermann in the 50s succeeded in providing such a third term, which depends on the electron's pressure and density. And the new induction equation, in which we appended this Biermann term here, is indeed able to generate a magnetic field from zero initial conditions, as long as the electron's density and pressure gradients are misaligned. This is simply due to the fact that the curl of this electromotive force is proportional to the cross product of these two gradients. And so this mechanism naturally creates the desired seed magnetic fields when only this condition is met. So that's why the Biermann battery has grown in popularity over the last decades, and it has been successfully invoked in several cases of magnetogenesis during the reionization era, which is an epoch of choice because it hosts that kind of misalignments between the electrons' density and pressure profiles. And so this is how we ended up adding the Biermann battery in the whole arsenal of mechanisms implemented in the Ramses code. I'll briefly describe how the implementation was performed. So the equation dictating the evolution of the magnetic field in the Ramses code is none other than the induction equation as described by the means of the electromotive force. And so I hence added the Biermann corresponding electric field to the EMF to account for the Biermann battery. An important structural property that has to be enforced at all times is the solenoidal constraint. Ramses being an AMR-based code, the most natural approach would have been to define the magnetic field at the center of each cell, where the other hydrodynamical variables are also defined. However, this procedure violates numerically the solenoidal constraint. And one way to solve this problem is, of course, to use the so-called constraint transport, which simply consists in writing the induction equation in its conservative form. And so following this prescription, the Ramses code no longer stores the magnetic field at the center of the cells, along with the other traditional variables, but it computes it on the faces of the cells. So in this framework, the total flux is defined at the edges of the cells, so that its circulation defines the B flux across the surface of the face. So this figure recaps where the quantities are defined with respect to the cell. This approach has the merit of fulfilling the divergence-free condition to the machine round of precision. And so as the EMF whose circulation defines the B flux lies at the cell edges, the Biermann term has then also to be defined at the edges. And in order to do so, I implemented two different methods. The first one, which we call the naive method, is the most straightforward one. Since the quantities involved in its expression, namely NE and PE, are located at the center of the cells, calculating EB at an edge requires averaging its value at the center of the cells sharing that edge. And on the contrary, the second method, which is more numerically stable, directly defines the Biermann term at the edge by using the values of the vertices bordering that edge. This will become clearer in a few minutes. This method takes advantage of the electron's equation of state. Numerical stability is indeed important because attempts to naively implement the Biermann battery can lead to the production of large non-physical magnetic fields, especially near shock waves, because the involved gradients can diverge at discontinuities, as they can increase without bounds with increasing resolution. This Biermann catastrophe is unfortunate because shocks furnish ideal sites for Biermann effects. And this second method circumvents the problem. This formulation of the improved method has the quality of ensuring that the generated Biermann field in an isothermal case is null at machine precision, because the electric field is then the gradient of a scalar, which is numerically zero. So that's why, thanks to the Stokes theorem, in a sense, we preserve a structuring property of the system at the discrete level. And so to summarize the two methods, here this figure illustrates how it is computed for the two different methods. So first, for the naive method, the orange cells here are used to estimate the spatial gradient of the electronic pressure at the center of the purple cell here they frame. And the electric current of Biermann is computed at the golden edge here by averaging the value of the four centered values of the purple cells. Whereas in the improved method, the orange cells are directly used to calculate the electronic pressure and temperature at the purple vertex here. And then the Biermann field is computed at the golden edge by using the purple and golden vertices that frame this edge. Okay, so I will spare you the numerical tests I conducted to ensure the stability of the method and directly jump to the actual results for cosmological simulations. So these simulations were conducted within the Sphinx framework, which feature realistic 3D environments. So we started with a small box of the size 2.5 moving megaparsec, and we look at the results at redshift equals 6, just after the epoch of reionization, which is, again, a prime epoch to host Biermann-induced fields within propagating ionization fronts, for instance. So just to have an idea on the structure of the box, here on the left is presented the gas density, where we can see the typical filament structure of the simulated galaxies. And on the temperature and ionization fraction maps, we can see that the medium is, as expected, nearly fully ionized after the EOR, with this small region here, which still did not have time to percolate. But on top of that, we can see bubbles in the temperature map, which correspond to the explosion of supernovae that translate into temperature of 10 to the 5, 10 to the 6 Kelvin. And so let's have a look at the resulting magnetic field that is generated from redshift 150 down to redshift equals 6. In the top figure here is presented a signed magnetic field map, which is a bit saturated in order to see the morphology of B. And as we probably have complicated temperature and density gradients we see that the sign of B constantly changes due to the cross product and tries to wrap the areas where magnetic fields are generated. And in the bottom figure here is presented unsigned magnetic field map to examine better the amplitude of the field. And what is striking is that we have kind of two distinct regimes. We have a low B mode around 10 to the minus 21, 10 to the minus 20 Gauss that follows globally the ionized regions. It has like a volume filling behavior. But on top of that, we have a high B mode here, around 10 to the minus 18, 10 to the minus 17 Gauss, that has a way higher amplitude. It seems to be concentrated around massive halos where supernova explosions occurred. So the important result here is that in addition to the classical Biermann channel associated with ionization fronts, we witness here another production channel, which is related to shocks. Its amplitude is way higher because of the increased temperature in such shock events. And the Biermann term is kind of proportional to the temperature.
3-minute warning.
Yep, okay. So when we look at the 2D histogram, we see that we have kind of a particular structure. So we see on the bottom row that we have very low magnetic fields, which can be associated to the pre-epoch of reionization linear perturbations. Maybe I will explain that afterwards if I have time. And on the top row, we can see the more classical behavior expected for large-scale magnetic fields, which is to say that it scales as density to the power of 2/3. This is an expected result. But what is striking is that this upper region spans over a large range of magnetic fields where it is supposed to be basically just a thin diagonal line. So let's zoom on this particular area. And that's what happens if we zoom and use proper colors. We see that in reality, there is not one diagonal line, but two of them. And both scale correctly as density to the power of 2/3. And this second new branch that we discover here on top of the classical one is related to, as I said earlier, to the propagation of shocks. And indeed, the amplitude of the fields in this high branch are as high as the fields previously seen in the hot bubbles, which again are generated by the high temperature supernovae, which is a nice result. And the two methods yield pretty much the same result, both quantitatively and qualitatively, which in a sense proves its robustness. Okay, and in order to assess that this high branch is indeed a byproduct of supernovae, we did a control simulation where we deactivated supernova feedback. And the result speaks for itself. Switching off the supernovae indeed turns off the shock-induced channel, which owed its high field value to the enhanced temperature in the hot supernova-generated bubbles. We checked that the same result occurred if we increase the box size. So 5 co-moving megaparsec box has exactly the same structure, but with more numerous events as the box is larger. With the three different regimes of the three different channels of magnetic field generation. And finally, if we look at the volume weighted average magnetic field strength and volume weighted average temperature for the different simulations, we can define two different epochs. As I said here, before the EOR, we have this linear perturbations, but I don't have the time to explain their origin. But here at the epoch of reionization, we can see the onset of the Biermann battery with a notable difference between the volume weighted average magnetic field without supernova and with supernovae. And so I leave you here with some takeaway conclusions. Thank you very much.
Thank you. Perfect timing.
Thanks. Just as a precision, all these results are presented in an article that was just recently accepted a couple of months ago. So if you want more details, you can read Attia et al. 2021.
We got a question from Patrick. So go ahead.
Yeah, hello, nice talk.
Thanks.
For an important problem. I mean, I think it was particularly clear from your picture that the magnetic field inside the supernova remnant is much higher than in the rest of the simulation. So I guess the obvious question is, do you think that at the end of the day, all those bubbles could kind of merge and I mean, they percolate and then produce high magnetic field compatible with what we see, or
yes, exactly. So this would be the natural follow-up of the work we conducted in this analysis. So to perform the simulations for a bit longer time and see whether they percolate or not. So normally they seem to start percolating when you look at the maps, because in the beginning they were just concentrated around the massive halos, and then they progressively expand and percolate. But as for the amplitude of the field, we expect the onset of some dynamo process, which is needed for the amplification of the field in order to reach the micro Gauss levels we see in galaxies. So the Biermann battery is only able to generate the seed magnetic fields that are really low magnetic fields, but we need an amplification mechanism. So typically turbulent dynamo within the galaxies in order to recover the magnetic fields we observe today.
Thank you.
Anyone else have a question? Yes, Yoki.
Hi, Omar. Great talk.
Thanks.
Can you go back to the plot where you showed the magnitude of the magnetic field as a function of time with the different simulations?
Oh yeah, this one.
This one. Why do you get a higher magnitude
Here?
in the larger volume simulation than in the smaller volume simulation?
So this is what we found out when we run the simulation, that we have like 1 order of magnitude higher magnetic field for the larger box. But the effect, aside from that, of changing the volume is not noticeable. And so we speculate, in a sense, that the difference of order of magnitude between here and here is that in the larger box, we have a bit of a finer resolution with respect to the larger, this is not correct. So we have larger halos, meaning that we start to resolve some kind of turbulent dynamo within the most massive galaxies. And that's why we could see the onset of some dynamo that amplificates a bit the magnetic field only in the higher box, but we did not really check that this was the case or not. This is just a speculation, but this is our educated guess about this.
Thank you.
Okay, great. I think with that, we're in very good time to move on to the next speaker. So,
hello.
Yes.
Can you hear me?
Yes, we can.
Okay, perfect. Let me share. Okay, you should be able to see the first slide.
Yes, we can.
Okay. Shall I start or shall I?
Sorry. Okay, so I'll introduce you. Okay. Next talk will be by José Canivete Cuissa, who will tell us about stellar magnetoconvection with Ramses.
Okay, thank you very much. So yeah, I'm José Roberto Canivete Cuissa. I'm a PhD student at the University of Zurich. And I've been working with Roman Tessier, my supervisor, in adapting Ramses to simulate stellar magnetoconvection. So convection, why studying convection? First of all, well, convection is one of the fundamental processes happening in stellar interiors. For example, for the sun, we know that it's responsible of carrying up the energy produced at the stellar core to the solar surface. And at the solar surface, it's also responsible for this granulation pattern that we can observe today. Convection is also important, for example, for the stellar evolution, global oscillations of the stars, and many other things. As, for example, also magnetic fields. So we know today that magnetic fields in stars must be sustained by some type of dynamo, large or small scale type. And in that respect, once again, turbulent convection zones play a fundamental role. Magnetic fields, of course, are very important in stars because they play a key role in their activity. So again, for the sun, we know that the magnetic fields are very important for flares, for mass ejections, and also for the solar wind. Of course, so convection and magnetic convection in general is a very complex topic, and it's characterized by highly nonlinear dynamics. So therefore, we are really forced to go to numerical simulations. So if you want to simulate convection, you should know that convection is characterized by very small amplitude perturbations or fluctuations around some kind of equilibrium solution. This equilibrium solution could be, for example, the hydrostatic equilibrium of the star. And if you want to simulate these with a conventional numerical scheme, you may run into troubles because the numerical scheme will introduce naturally some truncation errors. And it can be that the truncation errors are of the same amplitude or larger even than the physical perturbations or fluctuations that you want to study. Therefore, these truncation errors could simply wipe out all your physics, essentially. It also can be that these truncation errors introduce some waves in your simulation box that can even destroy your equilibrium solution, and which, of course, you would like to preserve. There are a few possible solutions to this. Of course, you can refine the mesh, but that's probably not the most smart way to do it because it can become very, very computational heavy. You have high order methods, and the approach that we choose to use here is to use well-balanced schemes. So the idea, so the goal of well-balanced schemes is essentially to impose implicitly in your numerical scheme a discrete version of the equilibrium solution that you want to preserve exactly. And the idea is to separate your variables in an equilibrium contribution and some perturbations around this equilibrium, and then impose directly in your numerical scheme the equilibrium solution of your system of equations. Very simple example here. I'm showing you the for the 1D hydrostatic equilibrium. We separate density, pressure, and velocities in an equilibrium component and a perturbation. And then you have an hydrostatic equilibrium equation that connects the equilibrium pressure and the equilibrium density. And then if you write down the momentum equation, you can essentially take out the hydrostatic equilibrium equation from the momentum equation. And what you're left with is a flux and a source term that depends only on perturbations of your variables. So you can see here just velocity, pressure perturbation, and density perturbation. This means that if in your system you have no perturbation, so just the equilibrium profile, you have no fluxes and no source terms, and your equilibrium will be automatically preserved. So now if you want to do this with a Godunov-like scheme, like the one we have in Ramses, you have to modify a little bit your numerical scheme. So what you have to do is to correct the source term, because as we have seen a moment ago, the source term will be dependent for the momentum equation, dependent only on the perturbations of the density. Same thing for the fluxes. For the momentum equation, again, only depends on the perturbations of pressure. And you also have to correct the interface interpolation, because if there are no perturbations, you want these two interface interpolations to match at the interface, so that there are no fluxes, so no waves propagating in your simulation that can destroy this equilibrium profile. And then finally, an extra trick that we use is to evolve entropy instead of internal energy, because essentially, the entropy is the main quantity characterizing convection. So we prefer to really have some more precision on this than the internal energy. And so we implemented this well-balanced scheme in both the hydro and the MHD models of Ramses. And now I'm going to present you some simulations. So we conducted a proof of concept for simulating magnetic convection with Ramses. Essentially, we tested the code and our implementation in a planned parallel stellar convective region that we took from this paper, Erwiger 2006. It's just a small box of a convection region, which you can see here at the bottom. It's in the profile of entropy. So we have essentially three regions, a bottom stable region, a convection zone in the middle, and then another stable region in the top. Each one of these regions is initialized with a polytropic stratification that you can see here for the density and for the pressure. We have a constant gravity downwards, an ideal gas, and we also had some artificial heating and cooling, an heating at the bottom of the convection zone to simulate essentially the energy coming up from the stellar interior, and an artificial cooling at the top of the convection zone to simulate radiative losses, for example. Then we run both hydro and MHD simulations with different resolutions. And essentially, if you do not put any perturbation in your simulation box, the code is able to preserve these equilibrium profiles up to machine precision. So if you want to trigger some convection, some turbulent convection, you really have to put in some perturbations. And that's what we did. So we put some percent level perturbations in density at the bottom of the convection zone. So this is what happens. So after 2000 seconds, we have development of some Rayleigh terror instabilities at the locations of where we put these perturbations. We have these plumes that develop that start to come to rise up. After a while, there is a second wave, let's say, of Rayleigh terror instabilities that develop at the top of the convection zone due to this cooling, this artificial cooling that we put in. And after a while, after 2000 seconds, we have a completely developed convection zone. So here I'm showing you the temperature perturbations around the temperature profile. And these temperature perturbations you can see are the order of 10 to the 5 Kelvin, while the temperatures, the true temperatures inside this convection zone are around 10 to the 7, 10 to the 8 Kelvin. So these convective perturbations are really of the order of percent per mil. So you see the importance of this well-balanced scheme. Here on the bottom, I'm showing you the evolution of the kinetic energy as a function of time for the 4 different simulations, the hydro ones. And you can see that after a while, that after the onset of convection, we have a growth of kinetic energy, and then it stabilizes. We reach a quasi-steady state where essentially the convection zone is fully developed. Here I'm showing you on the left the vertical velocity and temperature perturbations for a slice and horizontal slice near the top of the convection zone, just to show you again this granulation pattern that's quite similar to what we saw for the solar surface. And here on the right, I'm showing you the evolution of the kinetic energy power spectra for the different simulations. So the evolution is given by the shades of blue. So light blue means the early times in the simulation, and dark blue means towards the end of the simulation. And you can see that towards the end of the simulation, we recover this nice power, this energy cascade, which follows a Kolmogorov power law, which shows you once again the turbulent nature of the convection zone. So now let's go to magnetic convection. So let's put in magnetic fields. So we introduce very weak magnetic fields in the convection zone, and then we let the simulation evolve. And here in this plot, I'm showing you the magnetic energy in red and kinetic energy in blues for the different simulations once again. And you can see that the magnetic energies are exponentially growing at the beginning of the simulation, which is a clear sign of a small scale dynamo action. This growth rate is resolution dependent, as you can see. And after a while, once again, we reach a quasi-steady state where the magnetic field is essentially saturated, which with values that fluctuate between 10% and 30% of the equipartition value. Here on the left, I'm showing you again power spectra. So in red of the magnetic energy, and in blue kinetic energy for the simulations. Again, you see the magnetic energy growing up, and you see at the end of the simulation that there is a turnover scale where the magnetic field starts to dominate. This can be also observed in this plot, which is again an horizontal slice at near the top of the convection zone for the vertical magnetic field. And you can see the magnetic field is dominated by, is characterized by these strong small scale filaments with often very close mixed polarity filaments, which are concentrated in intergranular flows. So you can maybe notice that there are some granules, so regions where magnetic field is quite weak, and that the strong magnetic fields are concentrated in between these granules. These results are quite similar to what, for example, Rempel found in 2014 for simulations of the top solar convection zone. Here I'm showing you very quickly some probability density functions. So this is for the vertical velocity, this is for the horizontal velocity, and the vertical magnetic field and the horizontal magnetic field. This row is at the top of the convection zone, and this is more towards the bottom of it. And here the main message is just to notice that the velocity fields have this asymmetric probability density function, simply because of granulation. So we have different motions. We have odd, low density blobs that rise up, and then very thin downflows in between them. While the magnetic fields are more—
3-minute warning.
Thank you very much. While the magnetic fields are more symmetric, simply because they are generated through this turbulent small-scale dynamo, and therefore there is no preferential direction. These results are also quite similar to what we find in the literature for different convection zones. And we have a clear convergence of the results by increasing the resolution, as you can see from these plots. And here I'm going to show you the last result. So it's about waves, propagation in the top stable region. This is a KW diagram. Essentially, it's showing you the power associated with each wave mode in the top region. So here we have a moment, K and frequency, essentially. And just to show you here, we have some signal in this region, which is associated with pressure waves. Here we have a very nice ridge, a very strong ridge in signal, which is associated with gravity waves. And we have also some signal in this middle region here, which is associated with surface modes. So we can see that in our simulation box, we can retrieve these three principal wave modes that are excited because of convection modes that interact with this stable region. And this is also quite similar to what Herwig et al. Found in their original paper. So to conclude, we managed to implement a well-balanced scheme in the Ramses code that is it's able to deal with stellar magnetic convection. And we tested this implementation in a typical convection zone. Not very important which one, but the important thing is that we reach full developed convection zone after some time, that we have a very quite efficient small-scale dynamo action, and that we can follow also the wave propagation in the top regions. And in conclusion, essentially, we have the conversion with the resolution, which means that the code is working well, and also that the results are in agreement, qualitatively in agreement with the literature. So what's next? It would be cool to be able to simulate a full star or a full convection zone. Let's see if we manage to do this. We would like also to compare Ramses to other codes that are more like thought of simulated directly convection or magnetic convection. And also maybe study the interaction between magnetic fields and waves in this top stable region, because it's known that magnetic fields can interact with waves and suppress, for example, pressure waves. And with that, it's all. Thank you very much, and I'm happy to take any questions.
Thank you very much. Anybody got a question for Jose? Yoki.
Thank you for the nice talk. I am wondering, what's the role of radiation here? Is it okay to neglect radiation?
I think so. Yeah, in convection zone for sure. The convection zone is for sure negligible, I think. I don't know exactly the ratio between the convective flux and the radiative flux, but I think it's very small compared to the convective flux. If you want to simulate, for example, for the sun, if you want to simulate photosphere and chromosphere, then of course it plays a huge role. But we don't, I think we will not go towards that direction. We will go more towards probably core convection, so that photospheres and chromospheres and stuff like this, where radiation plays really a huge role, will not be in the model, let's say.
So is it because the radiation scatters so much that it just the flux is slower in a way? Is that it?
I think radiation plays a very important role in the heating layer and the cooling layer that are at the top and the bottom. That's key to the whole convection process, to have a heating layer at the bottom and the cooling layer at the top, and this is mediated by radiation. Yes, so we do it in a simple model here. Yeah. But if you want to do it more realistically, you could include radiation, and then you will have a more realistic heating and cooling layers.
And in the convective zone, is it just that the radiation is moving along so slowly in a way compared to the convective flux, right?
So in the convective zone, that's precisely because the radiation flux is really weak that you have convection. Because the temperature, if you want the entropy, if you don't have convection, the entropy will drop, will accumulate at the bottom, and the flux is kind of really weak. That's because of the opacity that appears like that. And so the radiation flux, which is very high at the bottom, suddenly becomes very weak because of the opacity that that becomes crazy. and therefore you can really neglect the radiation. But then it becomes strong again at the top of the convection zone, because then you radiate in vacuum and you have a very high flux. So in principle, you could do complete, it's clearly FLD, and we are clearly in the diffusion limit. Yeah? And you could do this with a full opacity, but it's an overkill in the sense that you don't really need radiation except at the bottom and at the top of the convection zone.
Excellent. Thank you.
Got a couple more questions, Patrick?
Yeah, nice talks, and nice to see that Ramses can do everything. One of the very difficult points when doing convection is the very small, the very high sound speed with respect to the relevant time scale. So usually people are struggling with inelastic stuff. It's quite horrible. I guess here you are using Ramses in a compressible mode, so which will be then a very severe limitation at the moment. Yes. There are methods like there is something developed at the Maison de la Simulation by Pascal Tremblin, inherited from I guess the nuclear department, which is a low Mach solver, which allows to deal with this kind of problem. I don't know whether it's something you have in mind, or how will you deal with this difficulty?
No, for the moment we are just using, as you said, the Ramses in compressible mode. No special tricks for that. So indeed, the simulation will take quite a while, especially with 512 resolution. We may try to use some implicit solver, but I think it will be too complicated. I guess Roman can add something on that. There are other methods like by artificially reducing the sound speed or the alpha speed in case, but for the moment we didn't modify anything in that respect. Also because it was just a test, so to see if we can retrieve some results that we find in the literature and if we have conversions of the code. If we go to full stellar boxes, then we may need some kind of clever trick to deal with that. Yes.
Okay. Good luck.
And maybe I can add quickly that what Roberto showed at the end with those waves, those pressure waves, right, is typically what you can do with this kind of code that you cannot do if you use anelastic kind of approximations or implicit codes too, right? Because you filter out those waves.
Yeah.
So here, one of the sweet spot of this kind of code, and there is a huge price to pay, of course, which is that you have to compute like forever, right? But the sweet spot is that you can deal with convective motions and look at their consequences in terms of acoustic waves. And so you can really do a lot of cool and precise wave analysis.
Yeah, a very interesting problem which require, I think, the compressibility and probably convergence in all its strengths, I would say, is when you want to treat stars which are still accreting. I think it's a problem which is essentially weakly treated at the moment, because then you have an accretion shock at the boundary of the star. So you need to have compressible stuff, and still you may have some convections that could then transport the energy of the shock into the star or not. I mean, how much is triggered in, has directed away. It's a very important problem for star formation in general, and maybe that could be attacked with this code.
And actually, it's a good point, because the technique we use for this well-balanced scheme can allow for an equilibrium solution that also contains a shock. So, of course, this equilibrium solution is not a hydrostatic equilibrium, obviously. You have a huge shock like coming from above, but this well-balanced scheme we use, you can actually introduce in your equilibrium solution a shock and a discontinuity, and it will deal with that.
Nice.
Johan, is your question quick?
Yes. What
Okay,
about thermal conduction?
Good point. I haven't computed the fluxes, but if I'm not wrong, I'm not using it in the code right now, right, Romain?
Yeah. So in stellar physics, thermal conduction is added to the opacity.
Yeah. So
there is no special role played by thermal conduction in stellar physics. It's just added to the radiative opacity, because it has the same grad T behavior, and you are in the LTE regime for the. So I mean, thermal conduction is included in the radiation that we don't include.
Okay, but you're developing perturbation to the temperature and thermal conduction in isotropic, so you have local effects in principle.
Yeah, but they're very weak, because the conduction coefficient is like the radiative opacity. They are both very, very weak, much weaker than the convective motions. So that's the whole point, right? All the conduction processes, whether they're radiative or thermal, they are all way too weak to transport energy, and that's precisely because they are weak that you have convection. So it's kind of a, there is some consistency. But if you include convection, if you include conduction, you need to include both radiative and conductive, like diffusion in the diffusion approximation. But it's not useful if you are, in the convection zone. It's fundamental, of course, if you are in the radiative zone.
Okay, I think we have to move on to the last speaker. Otherwise, we're going to break our nice track record of the day. Thank you, everybody, for good discussion. And our last speaker of the day is Pierre. He will tell us about fast methods to track brain coagulation and ionization. Off you go.
Hi, thank you. So I am Pierre Marchand. I'm a postdoc at the American Museum of Natural History in New York. I'll show you the fast methods I've developed to track brain coagulation and ionization with Vincent Guillet, Hugo Lebruy, and Mordecai Maclo. So as you may know, those grains represent about 1% of the gas mass in the ISM. But despite being only 1%, they are very important, particularly during star formation. So for example, for planet formation, including radiative hydro and transfer, non-ELM HD, or chemistry. So they are involved in many processes. And for each of those processes, their size really matters. Their size is really important because most of the time it's their surface area that's involved in those processes. And we know that during star formation, the grains coagulate. So they grow by sticking to each other. So this is a result by Vincent Guillet that shows the evolution of an MRN distribution here in purple. That's coagulating with increasing density and at densities of 10 to 12, which is about the density of the protoplanetary disk. The dust grains have grown from some micron to almost 10 microns. The problem is that grain coagulation, although it's not so complicated to compute by itself, it's a bit expensive to include in numerical simulations. Because well, the standard method to calculate the coagulation of grains is just to make all the size of grains, so all of your bins of your distribution interact with each other, and that's described by the Smoluchowski equation. And that depends on here this function k, which is the kernel, which represents the collision rate between the grains. And so it's complicated to do that for every cell in every time at every time step in your simulation. So we've found a new way to write this Smoluchowski equation with some algebra that's written in this form, where you have here the quantity of grain that varies as a function as only one variable that is a function of the environment, meaning the density and temperature. And then on the other side, you don't have any dependency on the environment, just a dependency on the grain variable, so its mass, its size. And what it means is that this variable, which we call chi, is the only dependency variable for the evolution of the grain size distribution. Another way to say this is that the coagulating size distribution will follow a unique path that's determined by chi. So it means that different environments, so high density where the coagulation is very fast, or low density where coagulation is slower, these different environments will not change how the grain coagulation is happening, the outcome of the coagulation. It will only change the speed. And so it's a 1D evolution that's entirely determined by chi. And so a coagulated size distribution is entirely determined by the initial size distribution and chi. So it can be a very fast method to track the coagulation of grains, because now in your simulation, instead of calculating the Smoluchowski equation everywhere, you just need to calculate this simple variable to get back to the size distribution. And here, it's an example for the kernel, turbulent kernel derived by Hormel and Cuisi. But it works for every kernel where you can separate the gas variable and the grain variable. So here is an example. So again, for the MRN distribution here in black, and the size distribution, coagulated size distribution for various values of chi. And what you can remember is that for this kernel, which is this form for chi, the coagulation starts to be very noticeable from chi equal 10 to the 17. Okay. And so the size distribution, yes, grows and grows to larger size. So here, say the MRN size distribution, because what's represented is the gas mass, the dust mass, sorry. The dust mass, not the dust number. So it's the minus 3.5 slope, but for the mass, so it's plus 0.5 initially. So how do you use this method? So before the simulation, you have to tabulate the distribution for various chi. So using a standard coagulation algorithm, using the standard Smolkovsky equation, you just do exactly like on the plot, just tabulate the distribution for various chi. And then during the simulation, you calculate chi, then you read or interpolate the table to get the distribution, and then you can do physics. So for example, in Ramses, it can be implemented as a passive scalar with a source term. So actually, it's not chi itself that's implemented as a passive scalar, it's the quantity rho chi. And so it's fairly easy to do and fairly cheap. And here is an example of a chi evolution during a protostellar collapse. So here we have evolution of chi with the density. And so chi increases with density as coagulation progresses further and further. And here is on the right the associated the mode of the distribution, so the peak of the distribution that I showed just before, corresponding to this chi. And what we see is that in the envelope of the collapsing star, the coagulation is fairly negligible. The grains don't grow that much, and all the growth happen at the highest density. Where in the disk, this is a very early disk, less than 1,000 years old. In the disk, the grain can grow from some micron to more than 10 microns. So this is a very good tool for tracking the growth of the grain. The main caveat of this tool is that it cannot be coupled with another method that changes the size distribution of grains, like fragmentation, for example. So that's the limitation for now. Now, I mentioned non-ideal MHD, and so I've developed the second method to calculate the ionization based on the model of Drain and Sutin that give the electric charge of grains. So this is this set of equations that are simply here an equation for the charge of grains. For an arbitrary size distribution, this equation gives the average charge of every grain size. So this is a bit the same for the polarization of grain. This one represents the equilibrium of the ion and electron flux on grains. This one is just the charge neutrality, and this one the ionization equilibrium. And actually, this system can be collapsed in just one equation with one unknown, and solving this equation with one unknown give you access to the number of ions, the number of electrons, and the average charge for every size of grains of your distribution. The main thing you have to assume to solve this system is the average mass of ions, which can be an educated guess, but the rest of the variable can be taken from directly from the simulation, like the density, the temperature, or the cosmic ray ionization rate. And it's also very fast to solve because it should take, on average, about 4 iterations of a Newton-Raphson method. So, so you can run it in Ramses. And here are the results of this equation. Just to show an example with here in black the fractional abundance of ions in black in solid lines and electrons in dashed lines as function of density, and in colors the average charge of grains for an MRN distribution. And here I showed only a few sizes. And so from this information, we can calculate the non-ideal MHD resistivities, and all the results are consistent with previous studies and more detailed models. What's upcoming is improvement of these tools. So I said that the coagulation method was not compatible with other methods that changed the grain size distribution. However, we know that, especially with the simulation by Hugo Lebris, that the dust to gas ratio is not constant throughout the protostellar collapse, and that dust tends to concentrate in higher density region and is more depleted in the envelope. And we are currently developing a method to include directly the variation of the dust to gas ratio in the chi variable. So to include, the physics will be a bit more complete in that sense. And also, a work in progress is the inclusion of the thermal ionization of species in the fast ionization model. The thermal ionization is very important because, especially in disks or in formation of the protostar, where you can reach temperature larger than 1500 K, the thermalization creates a lot of charged species, a lot of ions and so electrons, which make the non-ideal MHD resistivities drop by several orders of magnitude. And so it's important to include the thermalization to have a better description of the system and to describe the transition between non-ideal MHD environment to almost ideal or fully ideal MHD environments, like in the second Larsen core in the protostar.
3-minute warning.
Thank you. So these are my conclusions. So I've developed a fast method to track the grain coagulation, which allows to follow the growth of dust very inexpensively. And it's also mathematically exact. And we found, which is a preliminary result, but we found that the grains grow to at least 10 micron as they enter the protoplanetary disks. And also, I developed a second method to calculate the ionization inexpensively. And it allows the self-consistent calculation of non-ideal MHD resistivities. And of course, both methods can be coupled together, and they are now implemented into Ramses and are in the final test phase. So I encourage you to see the paper published earlier this year for more details. And also, if you want to use this method, the coagulation method, I encourage you to download the Ishinisan code to tabulate your size distributions. Thank you.
Thank you. Do we have any questions for Pierre? Patrick.
Yeah, hi, Pierre. Thanks. Nice. I think it's a useful work. So, as you said, it seems that the method cannot be is not compatible with the fragmentation of grain. Yeah. But as you know, it's likely the case that the fragmentations will be extremely important because the small grains are actually responsible of coupling the field and the gas. And if you have only coagulation, then you may end up with artificially high
yes.
resistivity. So what's the prospect of how can you deal with
that? For now, the best we can do is to limit the growth of the grains based on a fragmentation model. So if we are able to derive a fragmentation threshold for the grains based on their size, the density, whatever, we can limit the growth of chi, and that's actually what we're doing here. So based also on the fragmentation model of Hormel, I've been able to derive some dependency of the fragmentation threshold compared to the size of the grains and the density and temperature. And I limit the growth of chi based on this criterion. And so the result is an assumption that when we hit the fragmentation threshold, then there is an equilibrium between big grains that get fragmented and repopulate the small grains, and the small grains that recoagulate and recreate large grains. So yes, it's an assumption that's worth what it's worth, but that's the best we can do. And actually, yes, it's the case here. You may notice that the top of the distribution is fairly flat because it's due to this threshold that I derived, this function of density, a power law function of density, and so I limit the chi like this, which limits the growth of grain.
Why is it discrete Amax? It's because your
yes, sorry, it's the size. It's just the bins of the size distribution.
Okay, but in principle, if you have a very high resolution, yeah, okay.
Yeah, yes.
Any more questions? Sorry, I swapped the microphone. Any more questions? If not, I would like to thank all our speakers again. Thank you for a great series of talks.
Actually, I have a quick question.
Okay, go ahead.
If you're only interested in fragmentation, actually, so you're for example, you're in the low density ISM or during the collapse, and you're not really interested in the growth because, as you say, it's very slow. But you're only interested in fragmentation. Can't you do the same thing, but in the other direction?
Yeah, I'm trying to do that right now. I'm trying to see if there is a way to do that, and if there is a way to do that, which is not obvious, then there may be a possibility to couple both methods in some way, like having instead of having a chi dependency or 1D dependency, having a 2D dependency or grain size distribution. It would be possible to do that. I haven't looked too hard into this, but planning to.
Okay.
Well, can I ask another question? Along the same line. So I don't understand how you can. I mean, if you have inhomogeneous grain distributions, as you would if you treat dynamics, as you mix your grain populations coming from biocells, how is that compatible with this approach? This I don't understand.
Yeah, so the way we did it, let me share again, is that if you in the Smoluchowski equation, this well, actually this equation or this one, it's this one is a Lagrangian derivative of chi, and so yes, you have the chi depends on the grains and follow the path of the grains and summarize the path of the history of the grains. But then you just need to, if you multiply it by rho, it makes it just makes it a passive scalar, and it works actually very well. If you, because the equation of rho of giving chi here, we just imagine a derivative of chi equals with respect to time is equal NHT. It's a Lagrangian derivative, and from that you can calculate the Eulerian variations.
But it's true, I think Patrick's question is more related to the mixing. So if you have two different trajectories of chi that mix in the one cell, then you will somehow regularize the problem by, and the code will give you a mass weighted average of the two chi's. Right?
Yes, that's something like, yes, exactly.
Okay.
It's used in supernovae remnant physics, this technique to do chemistry after the facts. Sorry.
That's okay. I'm just aware that some other people, might be having other commitments. So if you want to continue discussing them, by all means, please go ahead. But I just wanted to make sure that there were any service announcements for tomorrow that everybody should hear, and then, you know, otherwise people are good to go. Anything from the organizers, or do we just say we see you back here tomorrow?
We see you back here tomorrow. The Zoom link is different again,
Yep.
so have a look at your email. And yeah, nothing special. We start at 9:30 like this morning.
Okay.
So have a nice evening, morning, or afternoon, depending on your time zone.
Exactly.
Thank you again.
See you tomorrow.